So hello friends, welcome back to my channel again. So today we are going to discuss about sleeve and cotter joint. Okay. So in previous class we have learned about the cotter joint. We have learned about the cotter joint and which is having spigot and socket. Today we are going to learn about sleeve and cotter joint. So for that, see here, what is a sleeve and cotter joint? To understand that one, first we will look at it this picture. So here we are having a diagram which is having a sleeve and cotter joint where we are having shaft 1 and shaft 2, which is having, this is the junction point, you can see this is the junction point. Okay, give me a second. So we can say, so what you can see over here is the junction point. Clear? Now you can see that this shaft and this shaft 1 and shaft 2 are connected by this extra thing, which is a hollow shaft, we can say. Inside that hollow shaft, shaft 1 and shaft 2 are inserted and they were fixed by using these two cotters, right? So this hollow shaft like thing what you can see over here is nothing but the sleeve. In the previous class, as we learned, there will be a socket and there will be a spigot is going inside the socket and we were using the cotter pin. But in this case we are having shaft 1 and 2 which is going inside the sleeve, and then two cotters are used to make those two shafts fixed in that position. So what we can say here is that, so that is what we have learned from the figure. Now, for that particular type of design, what are the data we are taking? The first thing we are considering here is that the there is a various proportions we can say for the sleeve and the cotter joint will be there in terms of diameter of the rod and the diameter of the sleeve. Okay, diameter of the rod means the shaft which we are using to join them. That is D, as you can see in the figure which I have shown you earlier. So if I consider D1 is the diameter of the sleeve, then it should be 2.5 times of the 2.5 times of the diameter of the shaft, or the shaft which we are going to join. And what is this D1? D1 is the diameter of sleeve, but it is the outside diameter of the sleeve. Similarly, we can say the diameter of enlarged end of the rods. So the rods are having some enlarged diameter. So that is D2. That is also called as inside diameter of the sleeve, should be equal to 1.5 D. These proportions we have to remember. Similarly, length of the sleeve should be is equal to 8D. Similarly, thickness of the cotter should be is equal to D2 by 4, which is nothing but the inside diameter of the sleeve, or else we can consider 0.31 D. 0.d2 by 4 or 0.31 d. Okay. Similarly, width of the cotter B will be equal to 1.5 d. Length of the cotter will be equal to 4d. The distance of the rod end from the beginning of the cotter hole inside the sleeve will be equal to, see here we can see this is A, which is nothing but from the end of this cotter to the starting of the sleeve. Similarly, from the end of the cotter to the end of the rod is C for both sides. Okay, so these are the proportions we have to remember. Now we will see what is the design procedure of this sleeve and cotter joint. So I can say design procedure of sorry. sleeve and cotter joint. We will see this one now. Okay. So what will be the first thing we have to see? We have to see how the rods are going to fail if the tension load is applied on that. So here we will consider the step 1 where it is going to give us the idea of failure of the rod in tension. The rods which are supposed to be joined, that is called as your failure of the rod if tension force is applied on them. Then what we know here? We know that the area of the rod is equal to how much? We know area is equal to pi by 4 d square. This is the area of the rod. Similarly, if we are applying the tension force, then if its permissible tensile strength is tensile stress is sigma t, then how much tensile load it can handle? The load it can handle is that, or we can say the tearing strength of the rod P is equal to pi by 4 d square area into permissible tensile strength. Okay. Sigma t. Okay, understood? So this is what is the tearing strength of the rod, or this is called as P also. Okay, here if P and sigma t is given to us, we can find out the value of D. Okay, then we will go for the second stage where we will be considering the failure of the rod in tension across the weakest section. Okay, across the weakest section. Okay, now what will be the weakest section of the rod? The area where we have made the hole for the cotter here. So out of the total area of the rod, suppose this is the rod, in this rod we have made this hole for the cotter. Then the area at this whole section will be how much? The area of the rod minus the area of the section, or the area of the hole we made for the cotter. So we can say weakest area of the rod weakest area of the rod will be equal to how much? As I told you, total area pi by 4 d square minus the area of the cotter, that is d into t. Sorry, d2 into t. Okay, d2 into t. This is the weakest section. Where we have made the weakest section, we have made in the area where the cotter hole is there, right? Cotter hole is where is the cotter hole? The cotter hole is made for the inside diameter or the smaller diameter of the rod. So it should be d2 square, d2 into t. So this is the weakest section. If we want to find out the strength of the weakest section, then P will be equal to area into stress. So area is equal to how much? Pi by 4 d square minus d into t into sigma t. So this is the failure of, in this case, if we know the value of p and t, we can find out here d2, which is the value we need for the dimension. Clear? Now here, if we want to find out d2, then we have to take the t value. So we can assume here t is equal to d2 by 4. Then it will be easy for us to find out the value of p. Also we can find out the value of d and d2 and t. Now we will check the crushing strength, whether the crushing strength for this dimension we are getting crushing stress that is falling in the safe value, under the safe value or not. Okay. So for that, what we will take? We will take the third step. In this third step, we can say failure of the rod or the cotter or cotter in crushing. In crushing. Okay. Now we know that where the crushing will be there. Crushing will be there where the cutter is there. So the if we consider the area of the cutter, then we can say area that resists crushing the area that resists crushing is equal to d2 into t. Right? Now crushing strength is equal to area into crushing stress. Already we know d2t and p value. Now we can find out the sigma c here, how much we are getting, and check whether it falls in safe region or not. If it falls in safe value, then it is the design is acceptable. If not, then the design have to be reconsidered. Okay. Now in the fourth step, what we have to do is that we have to check the failure of the sleeve. Okay. We will check the failure of sleeve that will be because of the tension. Because of the tension. Now, tension will be occurring in which area? That area which is resisting that area where the slot is present in the sleeve. So to find out the slot, it is a if it is a this is a hollow shaft. So hollow shaft will area will be equal to how much? Pi by 4 outer diameter square minus inner diameter square. So that will be the area of the hollow shaft. Out of that we are going to remove the portion where the hole for this cotter is done. Okay, so we will be getting area here. We can say resisting area will be equal to pi by 4 d1 square minus d2 square. This is the area of the hollow shaft minus d1 minus d2 into t, where we made the hole for the cotter, cotter pin. Now the strength will be equal to how much? P will be equal to area into the sigma t value. So area will be equal to pi by 4 d1 square minus d2 square minus d1 minus d2 t. This whole is going to be multiplied with sigma t. Sorry. This whole is going to be multiplied with sigma t. sigma t. Okay. This here what we can find out, the value of d1 can be find out over here. Clear? This is what is the step number 4. In step 5 what we will do? In step 5 we are going to check the failure of the cotter that is due to shear. Okay. Failure of cotter due to shear. Due to shear. Now, where the shearing will be occurring? The shearing will be occurring in the cotter region. And how many areas the shearing will be there? 2 areas will be there, because this is the cotter will be there, no? This cotter is having the sleeve area and also the shaft area. So, the junction point of sleeve and shaft in the top and the bottom both will be experiencing the shear. That's why we have to take the double shear here. So if we have to take double shear means double area, therefore resisting area will be equal to area will be equal to 2 into width of the cotter into its thickness b into t. Okay. Now what will be its strength? Its strength will be equal to, because it is going to fail in shear, so we have to consider the shear stress here. So P is equal to 2bt into tau. Here we can find out the value of B. Okay. So here we can find out the value of B. Now, in the next step, what we will do? We will consider the failure of the rod end in shear. Failure of rod end in shear. Failure of rod end in shear. If we consider this one, then we have to consider in the rod end which area is experiencing the shearing stress. So which area here considered? If we go for the diagram, you can see here the diagram. In this diagram, this is the rod end where shearing will occur, will be in this region of A. Okay. Which area? This area is going to experience the shear. This area going to experience the shear. So if we consider this area, then the strength we can find out there. So here I can say resisting area is equal to 2 into A into D2. Okay. So this is the area where shearing of the in the rod will be there. Now for finding out the shearing strength, P will be equal to 2 A D2 into tau. This is the shearing area. This is the area where shearing will occur, and in this case we will be able to find out the value of A. Okay. Similarly, in the 7th step and the last step, we will consider the failure of the sleeve in the shear. Okay. So the area for this one will be equal to how much? So I can say resisting area is equal to how much? Resisting area is equal to D1 minus D2 into C, and here also double shear. So 2 into C into d1 minus d2. Therefore, the resisting force P is equal to area d1 minus d2. I can say P is equal to d1 minus d2 into 2C into, it is a failure in shear, so tau. So here what we can see, we can find out, in this case we can find out what is the value of C. So all our dimensions are claimed here. So design is over here. So we will see a problem now. So this is the question given here. Design a sleeve and a cotter joint to resist the tensile load of 60 kilonewton. All parts of the joints are made up of the same material with the following allowable stresses. Sigma T is equal to 60 megapascal, tau is equal to 70 megapascal, and sigma C is equal to 125 megapascal. So I can say what are the given data here. So given data is equal to, first thing given 60 kilonewton. So P is given 60 kilonewton. Sigma T is given 60 megapascal. Tau is given 70 megapascal. Sigma C is given 125 megapascal. Okay. Now, what we have to find out is, it is saying you have to find out the value of your different parts of the sleeve and sleeve joint. So we'll go for the first step. First step is in first step what we will find out? We will find out the diameter of the rod. So for diameter of the rod, what we know the formula? P is equal to pi by 4 d square into sigma t. Pi by 4 d square sigma t. Now we know here P is equal to 60 kilonewton. Convert into Newton is equal to pi by 4 d square. D is not known to us. D is not known to us, and we know the value of sigma t is 60. Okay, therefore here D will be equal to how much? We will be getting 35.7 around. So we can take next even number, that is 36 millimeter. Okay, this is the first step we got. In the second step, we are going to find out the diameter of enlarged end of the rod and the thickness of cotter. That means we are going to find out the value of D2 and the value of T. Okay. So in the next step, what we will find out? The diameter of the enlarged diameter. Right. So for enlarged diameter, we know that in the second step, we know that P is equal to how much? We know that P is equal to pi by 4 d2 square minus d2 into T into sigma T. I can say assume T is equal to how much? We can assume that T is equal to d2 by 4, or we also know that dt is equal to taken 0.31 of d. right? So we are not going to go for that complicated one. We will directly get here that 60 into 10 to the power 3 megapascal in your Newton is the value of P. Pi by 4 d square is not known to us, minus instead of t we put d2 here is equal to, instead of t if we put d2 by 4 here we will get d2 square divided by 4 into sigma t, that is value of sigma t of value is 60 megapascal, right? Now here we can get the value of d2. Let's find out how much we are getting d2. So we will be finding out d2 is, we got 20.43.2. d2 we will get 43.2 approximately. Next even number 44 mm. If d2 is equal to 44 mm, then t is equal to 44 divided by 4 is equal to 11 mm. Okay. Now we will check this value with the crushing strength. So we know that for crushing strength formula is equal to P is equal to D into T into sigma T. So D2 into T into sigma C. So here we will get sigma C is equal to how much? Sigma C is equal to 123.96. So we will get 123.96 which is almost equal to 124. Which is almost is equal to 124 megapascal. How much it is given to us in given data? In given data it is saying sigma C should be 125 megapascal and it is falling below to that, right? It is below to 125 megapascal is given data. Hence our design is safe and we need not to recalculate or calculate the dimensions again. Now we will find out the outside diameter of the sleeve. To find out the outside diameter of the sleeve, what we have to take is the formula. In the third step, we can take the formula is P is equal to P is equal to pi by 4 d1 square minus d2 square minus d1 minus d2 into t, and this whole is going to be multiplied with sigma t, right? So here we will get the value of d1 because we already know p is equal to 60 into 10 to the power 3 is equal to pi by 4 d1 square minus d2. We found out how much? We found out d2 is equal to 44 mm, right? Minus 44 square minus d1 minus 44 into 11. This whole is multiplied with sigma t is equal to 60. So here by applying Siddharacharya rule, we will be able to get the d1 value is 58.4, suppose 60 mm. This is the diameter of the sleeve we got, outside diameter. Now we will find out the thickness of the cotter. So to find out thickness of the cotter, we have to make sure that there will be the shear strength of that cotter should be equal to the maximum load applied. So we can say P is equal to 2B into T into tau, which is equal to B will be equal to P is how much? 60 into 10 to the power 3 divided by tau is 60. Sorry, tau is equal to how much? We got 70. Tau is equal to 70. 70 megapascal into T we got 11 and 2. So we will get B is equal to how much? We will get B is equal to 38.96. 38.96 almost equal to 40 mm. Okay. Now we will find out the value of A and C. For finding out A, again we have to consider the double shear in the rod. Now, therefore, now we know that P is equal to 2A D2 into tau. So, A is equal to P 60 into 10 to the power 3 divided by 2 into D2 44, tau is equal to 70. How much we get? We will get here suppose 9.74, which is supposed to be equal to 10 mm. Similarly, P is equal to how much? We know that P is equal to 2 into d1 minus d2 into C into tau. Here again by putting all the value other than C, we get C is equal to 26.78, supposed to 28 mm. .78 supposed to be 28 mm. Here ends your cotter joint with sleeve and cotter joint. Okay, I hope you have understood this one. If any doubt, you can WhatsApp me. Okay.